So this lecture is using Coulomb's law. It's a continuation of the previous one, but now we're going to look at the superposition principle, and we're going to look at electrostatic forces in 2 dimensions rather than just 1 dimension. So it says here that all forces, including electrostatic forces, are vector quantities and obey the laws of vector addition. So the equation describing Coulomb's law uses only scalar quantities with the understanding that the direction of the force always lies along the line joining the center of the 2 charges. So these are vector addition problems, but we always have to consider the direction based on whether these charges are opposite or the same to determine where that force will act. Is it going to the left, to the right, up, or down? So the superposition principle basically means that if we have a charge that's experiencing forces from other charges, the net force on that single charge is the vector sum of the separate electrostatic forces. So it's a superposition of all those forces together. Now, if these charges are in a straight line, this is a one-dimensional problem. We just add or subtract. But when we are involved in 2 dimensions, we have to do the vector addition, and you have to use some trigonometry or the Pythagorean theorem to end up determining what the net force would be. So here's a sample of a problem in 1 dimension. We have 3 charges. We have a Q1, a Q2, and a Q3. 2 are negative, 1 is positive, and they're located as shown. And we're asked to calculate the net force on Q3 due to Q1 and Q2. So now we can see the problem, and basically what we need to do here is we need to find out the force of 1 on 3. 1 is the one on the far left, 3 is the one in the middle. Which is going to be, of course, k q1 q3 over r13 squared. And we need to find out the force of 2 on 3, which is k q2 q3 over r23 squared. So with those 2 values, we need to solve that. And then we need to find, using the superposition principle, the net force on 3. This value here, so you might be tempted to put in a -2 for Q1 and a -1.8 for Q2. I'm going to tell you to not do that and just use the idea that we can determine the direction based on whether these are alike charges or opposite charges. 1 is a positive charge, 1 is a negative charge, 3 is a positive charge. So that means that for 3, because this is the force of 1 on 3, but I'm really interested in what the force on 3 is going to be from 1. So 3 is going to be moving towards 1. So this is going to be going to the left when we're all said and done. And this one is going to be going to the right because 2 is on the right of 3. 3 is going to be moving towards 2. So that means that our direction here is to the right. So let's solve these now. K, of course, is 8.99 times 10 to the 9. Q1, I'm just going to write it as -2. The micro is 10 to the -6. Q3 is 1.5. The micro is 10 to the -6. The distance between is 1.5 in this case. On this side, we have 8.99 times 10 to the power of 9. Our Q2 is -1.8 times 10 to the -6. Our Q3 is 1.5 times 10 to the -6. And our R distance between, it's 4 minus 1.5, so it's 2.5 squared. So let's figure out what both of these are. 8.99 times 10 to the power of 9 multiplied by, I put in -2, I'm sorry. Even I get tempted here and I'll put in these negatives, but make these both positive because we've already determined here with the direction so that we can just use magnitudes in this. So multiply this by 2 and by 10 to the power of negative 6. Multiply by 1.5 and 10 to the power of negative 6. And then divide by 1.5 squared. And we end up with 0.11987. In fact, actually, it's 0.0. That's newtons to the right. I'm not rounding yet because, sorry, that's newtons to the left, and I'm not rounding yet because we're going to need this to calculate our net force. So in fact, I'm going to save this in my memory. And then I have 8.99 times 10 to the power of 9 times 1.8 times 10 to the power of 6, negative 6, times 1.5 times 10 to the power of negative 6. Negative 6 divided by 2.5 squared. And I get 0.0038884 newtons to the right. Now I need to find the net force, which is the vector addition between F23 and F13. We will take left as positive because that's the larger. So I'll write this in as 0.011987 plus a negative 0.0038884. So this value here, I'm going to make that negative and add that to what I had in my memory. I end up with 0.0081. I'll just stop there for two significant digits, which can be written as 8.1 times 10 to the negative 3 newtons to the left, which is my answer for this question. Okay, so let me switch this back here. I'm going to turn this off rather, so that we can go down to the next question. So this question here now says that the same charges, we're using the exact same charges here, but now we're asked to find the force on Q2 due to Q1 and Q3. So here we have, it's the same general idea. Q2 is the one on the far right. So the force of 1, move this so that we can kind of see here. The force of 1 on 2 is K Q1 Q2 over R12 squared. And the force of 2 on 3 is K Q2 Q3 over R squared. I think we've already calculated that, but now we have to find out what the distance is. So let me just pull it up here. Q2 on 3, which was calculated previously. There's the question. Q2 on 3 was this value. So I'm just going to write that in here. 0 equals 0.003884 newtons. In this case, though, 2 is on the right, 3 is in the middle. 2 is going to be attracted to 3. So whereas in the previous one what we said was that it was moving to the right, because 3 was moving to the right, which was where 2 was located. Here 2 is going to be moving to the left because that's where 3 is located. So this is a force experienced to the left. And in this case, this is a repulsive force because 1 is negative and 2 is negative. So this will also be a force to the left because 3 was moving to the sorry, I meant to say to the right. 3 was moving to the left because it was attracted to that. 2 is going to be moving away from 1 because they are repulsive to each other. They're both attracted, or they're both the same sign. So this is 8.99 times 10 to the power of 9 Q1 is 2 times 10 to the negative 6, and Q2 is 1.8 times 10 to the negative 6. The distance between these is actually 4. So this becomes K, which is 8.99 times 10 to the power of 9 times 2 times 1.8 times 10 to the power of negative 12. I'm just going to do that step together. Divided by 4 squared. And this gives us a value of 0.002, 02, all right, newtons to the right. Now I have to find the net force. So F net of 2, this is going to be the vector addition of F12 plus F23. I'm going to take left as positive because it's the larger value. So this is negative 0.00202 plus 0.003884. So I would negate this and add it to 0.003884. I end up with a value of, rounding for 2 digits, 1.9 actually, times 10 to the negative 3. And this was going more to the left than to the right. Oh, sorry, there was a newtons in there. So that would be the solution to this problem. And actually, I just have to correct that it is 3 significant digits for this question. Just like in the previous one, it was 3 significant digits, but for some reason I thought it was 2. So make sure that negative 2.00, those are 3 significant digits. 1.80, 3 significant digits. 1.50, 3 significant digits. So for both those questions, we should have had 3 significant digits. Next here we have 3 charges that are arranged in a triangle. So this triangular arrangement means that the net charge on C is going to be it's not going to be just in a direct line. It's going to be pushed down by A because they are it's being repulsed by A. They're both positive charges. And it's going to be pushed to the right to B because they are opposite forces, so it would be attracted. So let's work on solving this, and I'll try to keep that triangle up.
Mr. Sadler, please contact the main office. Mr. Sadler, please contact the main office.
So let's work on this, and what we can see here is that we'll have to find f of A on C and f of B on C. So f of A on C is K QA QC over RAC squared. F of B on C is K QB QC over RBC squared. And I won't write in what the K is. I'm just going to write down these values here. But actually, we should do the direction first. A is going to be pushing C down because they are both the same sign. B is going to be pushing C to the right because they are attracted to each other. And this is going to be K. QA is 5 times 10 to the negative 6. And C is 3 times 10 to the negative 6. And the distance between them is 5 centimeters. Sorry, 0.05 squared. Here I've got K. I'm not going to write down K again just because it makes it easier. QB is 2. I'm not writing negative 2, just 2. I'm taking just the magnitude. QC is 3. And this is over 2 centimeters. So now, to find out what both of these are, I have 8.99 times 10 to the power of 9 times 5 times 3 times 10 to the power of negative 12 divided by 0.05 squared. I end up with a 53.94 Newton force, and that is going to be going down. On the other side, I have 8.99 times 10 to the power of 9 times 2 times 3 times 10 to the power of negative 12 divided by 0.02 squared. And here I have 134.85 newtons. This will be going to the right. So now I have to do a vector addition to find out what this value is. So F net is FAC plus FAB. It's the square root of 53.94 squared plus 134.85 squared. So this value squared plus 53.94 squared and squared, and the square root of that is 145. That's newtons. I'm going to have to round that to significant digits, so I'll write it down here because there's two significant digits here, is 150 newtons. I'll also have to find the angle, which is the inverse tangent of the smaller value, the 53.94, over the larger value, the 134.85. So 53.94 divided by 134.85 is 0.4, and if I find the inverse tangent of that, I end up with 21.8 or 22 degrees. So this goes, this is 22 degrees. It's going to be going to the larger value first is here. So it's going to go to the right and then make a 22 degree turn down. So this is my solution here. 150, right 22 degrees down. I know they used east and south in your answer. In the lecture, but it's kind of odd to say east and south when we're talking about things that are so small. So I prefer right and down. Although you can do it either way, I'd mark either of them correct. So and that's it for this lecture. Try out the homework, and again, let me know if you're having any difficulty.